Modern large language models operate through billions of parameters that dynamically process uncurated text. Because these models interpret every input as a probabilistic sequence rather than static code, the logic of traditional software firewalls fails to map onto the system's architecture. Vulnerabilities in these systems align with specific phases of the model's operational lifecycle. The machine learning timeline flows from data collection and distributed training to the deployed model processing a user prompt. Pre-deployment exploits are causative attacks, altering foundational weights. Post-deployment, the threat shifts to exploratory attacks, where crafted inputs bypass the system's guardrails. Looking at this threat taxonomy matrix, we see attacks target two distinct areas: model integrity, forcing the model to produce malicious outputs, and data privacy, extracting sensitive information hidden within the training set. Defending these models requires mathematical exploits across this entire timeline to deploy phase-specific countermeasures. Training an LLM requires ingesting billions of tokens from the open internet. Relying on uncurated, web-scale data introduces an inherent vulnerability to data poisoning, as malicious samples are easily included in the primary training set. In a backdoor attack, adversaries merge triggered malicious instances into the clean dataset. The model behaves normally, but executes a malicious action upon encountering a hidden trigger phrase. Attackers also utilize front-running poisoning. By injecting temporary examples into platforms right before a dataset snapshot, poisoned data is indexed permanently. To filter out these poisoned inputs before training begins, engineers deploy anomaly detection. These algorithms identify poisoned embeddings by measuring inconsistencies in sentence-level semantics, or flagging unexpected spikes in text perplexity that indicate a non-fluent trigger phrase. While anomaly detection effectively flags statistical outliers, the scale of uncurated data pipelines makes guaranteeing absolute training integrity a persistent challenge for engineers. Model training is distributed, with multiple GPU nodes computing and exchanging gradient vectors with a central parameter server. In a gradient leakage attack, a rogue participant intercepts these vector updates to reconstruct private training data. Using the deep leakage from gradients algorithm, the attacker feeds dummy inputs to produce dummy gradients. The algorithm continuously minimizes the mathematical distance between these generated dummy gradients and the real intercepted gradients. This optimization loop eventually forces the dummy data to perfectly match the private original text. To stop this, engineers use differential privacy. By injecting calibrated noise into the gradient computations, they ensure that the presence of any single data point does not statistically alter the output. However, in LLMs, there is a direct inverse relationship between these privacy guarantees and model utility. Injecting enough noise to secure the gradients significantly degrades the model's performance, forcing a compromise between mathematical security and baseline network accuracy. Once the model is deployed, the threat shifts to exploratory techniques like prompt injection and jailbreaking, which target the integrity of the model's responses. This occurs because LLMs operate as autoregressive interpreters. They lack a mechanism to differentiate between authoritative system instructions and the raw data provided by a user. As shown in the prompt injection formula, malicious instructions embedded in user data can override the system's intended task vector, causing the model to follow the attacker's command instead of the developer's. To defend against this, system architects deploy structural prevention mechanisms like retokenization. Using BPE dropout, the system randomly drops byte pair merges during tokenization. This breaks adversarial token strings into smaller, unexpected subwords, destroying the malicious sequence before it reaches the embedding layer. Against jailbreaks, architects apply randomized smoothing via Smooth LLM. The system duplicates a user prompt into multiple perturbed copies running in parallel. A majority vote filter aggregates these outputs. Because jailbreaks rely on fragile phrasing, random noise breaks the exploit in most copies, neutralizing the anomaly. Securing inference integrity requires shifting from behavioral guardrails to structural perturbations that modify the input before the model ever processes it. Inference stage privacy threats include data extraction, membership inference attacks, and embedding inversion. When an LLM overfits, it assigns disproportionately high confidence scores to text sequences from its training set. Adversaries exploit these confidence intervals to map and extract verbatim private data. This is the formula for perplexity-based detection. Perplexity measures how well a probability distribution predicts a sample. Machine-crafted adversarial prompts predictably spike across this perplexity threshold. By monitoring for these high-entropy signatures, the system can trigger an immediate block. However, adversaries can also target the vector space. In an embedding inversion attack, an attacker targets the front end of the model to reverse engineer numerical embeddings back into the original private text. Dimensional masking stops this by overwriting the first dimension of the embedding vector with a constant language identifier. This misaligns the interpretation of the embedding just enough to disrupt the inversion process. Protecting data privacy at inference requires combining this architectural obfuscation with continuous statistical monitoring. This matrix maps the efficacy of every primary defense against the known taxonomy of LLM attacks. High-efficacy interventions, such as pairing retokenization with jailbreaks and dimensional masking with embedding inversions, have proven the most successful. These solutions are effective because they structurally alter the model's ingestion pipeline, enforcing mathematical boundaries that behavioral guardrails often fail to maintain. However, certain vulnerabilities currently lack any proven countermeasures. Black box model inversion attacks, for instance, remain a significant unmitigated threat. These gaps suggest that standard system prompts and basic reinforcement learning are mathematically insufficient to secure a deployed model from a dedicated adversary. Securing large language models requires a transition toward multi-layered structural interventions integrated across the entire machine learning lifecycle. Understanding the engineering and implementation behind these systems is the first step in building more resilient AI. To continue exploring the mechanics of data science and artificial intelligence, subscribe to the Learn by Doing with Steven channel. For deeper explorations into machine learning architecture on the go, join us on our audio platform. You can find the Steven Data Talk podcast on YouTube Music, Spotify, and all major podcast platforms. We are committed to providing technical breakdowns of the data systems shaping our world. Thanks for watching.